Okay, YouTube, in this video we're going to talk about basically the unique property of all inverse functions, and that is that they undo one another. And so generally speaking, let's recall that with some function, we're talking about functions of angles, trig functions these days. We get some value here. Our inverse trig function, which is f inverse of, and I always want to write an angle there, of some value is actually spitting out some angle. And so certainly we've been referring to these inverse trig functions like this, sine inverse of x maybe equals some theta. What I want to do is I want to kind of generally describe this here. We've seen finding inverse trig functions in the past that we have some original function, and I should have called this f of x. I'm going to call this f of x. We'll call this f of x. But this original function where y equals the sine of x, and if we wanted to find the inverse of it, truly all we need to do is to switch the domain and range, switch the domain and range. And so when doing this, we're really just taking the x value and switching it with our y, and our y value switching it with an x. So we get this. We get x equals the sine of y. Now, to be in, kind of like an appropriate form here, we often agree that we're just going to get this y value by itself. But here's what I'm going to tell you. The neat thing about inverse trig functions is that they truly do. They do undo one another. So if I said f of f inverse of theta, we would get theta, or, sorry, that'd be a value here. A value, f inverse of a value, okay, then I would just get the value, okay, fun story. And if I were to do f inverse of f of theta, I would just get theta. That's a theta, you guys, theta, sorry. But basically, you can see that these inverse trig functions, they undo one another. And I'm going to get those strike marks off there for a second. But here's what I want you to see. If they undo one another, then with this equation right here, what we'll do is we're going to take sine inverse of both sides. Try to squeeze this in here. And so when we do this, we're going to say sine inverse of everything on the left. And we get this x right here. And so we'd say, okay, so sine inverse of everything on the left here. And that's the same thing as sine inverse of everything on the right. And when we do a sine inverse of the sine of y, funny story is that these sine and sine inverse functions cancel out. And so what we really get is this. We get sine inverse of x is really truly equal to y. And so this is our inverse trig function right here. Essentially though, one thing that I do want to mention is this. Now remember, with our inverse trig functions, when we take the inverse trig function of something, it's always going to give us an angle. And the thing here is this. The angle that you get is always kind of restricted. It's between, two different values. And so when it comes to this, basically what I want to mention is this. When you take the sine of any angle, these always cancel out, and you're just going to get what's left inside of here. Like this always works. Basically, we'll say this. When you take an original trig function of an angle, sine of an angle, cosine of an angle, tangent of an angle, you're always going to get something back, with the exception being tangent. We have some undefined spots here, but you're always going to get these to cancel out. But when you take the inverse trig function of something, okay, it's going to be restricted in what it can give you. And so basically what I'm telling you is, look, we're taking the arc sine of the sine of y. You would naturally think these cancel out. And they somewhat do, but what I'm going to tell you is this. You get some value y. And here's what I'm going to show you. When you take the inverse trig function of all of these values here, the sine of sine of an angle, cosine of an angle, tangent of an angle, whatever, you're going to get some y value. But with respect to sine inverse, remember that we always get an angle between negative pi halves and pi halves. And with respect to cosine inverse here, we always get an angle between 0 and pi. And with respect to tangent inverse, we're always getting between negative pi halves and pi halves, but not including those values here. And that's exactly what you're going to see here. So when we do our sine inverse, basically what we're saying is, don't forget, you have to give me an angle between negative pi halves and pi halves that makes this true. And don't forget with cosine inverse, you have to give me an angle between 0 and pi that makes this true. And don't forget with tangent inverse, you have to give me an angle not only between negative pi halves and pi halves, but not including those whatsoever. So I'll put open dots there, and I'll even put closed dots on these guys here just to emphasize that these are the outputs we're going to get. So with this last part of this video, we just want to look at some basic property that says, look, sines and sine inverses, tangent, tangent inverse, cosine, cosine inverse, they cancel out. They like undo one another. We just have to be careful with the values that we get. So first things first, when we look at this one here, we say tangent of arctangent of negative 5. What I want to write is that we are taking an original, oh, let me write on this, please and thank you. We say we're taking an original trig function of its inverse. And if that's the case, original trig function of something, they simply cancel. Sorry for the handwriting. So whenever you take you know, like tan of arctan of -5 here, we would just say that these cancel out, you just get -5. I'm not even kidding you. Like that's how easy it is. And that's the property of inverse trig functions that we want to highlight here. Same thing here, except for now, what I want you to notice is that we are taking, check this out, an inverse trig function of an original trig function. Dun dun dun. So when we take an inverse trig function, I say inverse function, inverse trig function here. Sorry for the writing. Inverse trig function. And then just make this clear here. We say beware, beware. Basically what I mean is this. When we do this, what we're going to do is we are going to evaluate the inner function first if we can. I'm actually going to say this here. We're going to evaluate first. And here's what we know. As a matter of fact, we say sine of 5 pi thirds. We say sine of 5 pi thirds. What would we get? And so let's go ahead and sketch our 5 pi thirds radian measurement here. We know that 1 pi third is a 60, so 5 60-degree angles will put us down like 300 degrees in degrees. This is our 5 pi thirds right here. If we were going to do this, of course, we would just use the reference angle anyways. And so we say our reference angle here is just a positive pi thirds. And so what do we know about the sine of a positive pi thirds? Well, on our unit circle here, up here, we'd say that these would be both over 2. And as we count down on the left here, we usually go 1, 2, 3. So going back up on the right, we go 1, 2, 3 on the top here. We say, okay, so what's true about the sine of 5 pi thirds? Well, it would have to be the same as root 3 over 2. So we get root 3 over 2, root 3 over 2. But what I notice here is that it's negative. Okay, down here we would have a negative y value. So we have to say, or we could have just said, you know, all students take calculus. We just evaluated for sine in the 4th quadrant. And the only thing that's positive down there is cosine. So we say, look what you get negative root 3 over 2. So now what we're going to do is evaluate first, rewrite second. And so 1, evaluate first. 2, rewrite second. What I mean is this arc sine of 5 pi thirds is the same thing as the arc sine of negative root 3 over 2. So now we're asking this question, check this out. Hey, what angle are you? What angle are you? That gives you a sine value of negative root 3 over 2. And what we got to remember here is sine inverse is only defined, guys, as giving you an output between negative pi halves and pi halves. And so we say, well, what angle is it that my sine value is negative root 3 over 2? I can clearly see that it's this angle right there, right there. But we say, what angle is this? We have to write that it's a negative pi 6 or pi third or a negative 60-degree angle. So what we get here is this negative 60 degrees or negative pi thirds. So the important bit here is this. This is going to happen every once in a while. You notice that we had the arc sine of the sine of an angle. Okay, here's what I want to point out. These don't just cancel out perfectly and give you 5 pi thirds, because I know that the arc sine of an angle could never be 5 pi thirds. It has to be between negative pi halves and pi halves. So here's what you got to remember. Original trig function of an inverse trig function, totally awesome most of the time. You don't have to worry about it. Kind of like down here. Cosine of cosine inverse of pi. Pi. Told you. Told you. We took an original trig function of an inverse. But when you take an inverse trig function of an original, remember this. Evaluate the inner part first using what you know about your unit circle, and then go back and ask this question here. Now what angle between, you know, your restricted values there for outputs gives you this? So this last part, this is going to be interesting here. You'll notice that we have a tangent of an inverse cosine, and we have a cosine of an inverse sine. And these don't cancel out perfectly. Why? Because these are not inverses of one another. Tangent is not the inverse of arc cosine, it's the inverse of arc tan. And so these won't cancel out at all. But we're going to go back to this idea that what we're going to do is evaluate the inside first and then rewrite second. So here's what I'm going to suggest. When these don't match, non-matching functions, inverse functions, functions with respect to inverses is what I mean, to inverses. And I'm not really sure you know what I mean there. I'll tell you what I mean. Basically, because these aren't the same type of function. You know, it's not tan and tan inverse, tan and arctan, because they're different. What we're going to do is this. We're going to sketch this angle first. Sketch the inner angle first. What I mean is this. That is an angle. This is some angle theta. So we're going to be really clear on this. And so what I mean by this is that we're going to say that it's some angle in standard position. And since I get to choose any angle that I get to sketch, you know, that I want, what I'm going to do is I'm essentially going to say that I think my angle terminates in the first quadrant. You know, I can do this if I want. So here's the cool thing about inverse trig functions. We said this is theta, but remember theta is this angle r cosine of 2 over 3. And so I'm not going to write r cosine of 2 over 3. I'm going to say cosine inverse of 2 over 3 because I don't have a lot of room. But the coolest part about this, you guys, is here we go. Remember we would have some point xy on the terminal side. Good deal. Here's what I already know about this. When you write your angles as inverse trig functions, it's quite literally telling you two sides of a right triangle. And drawing this picture, I could say, it's saying I am the angle that when you took the cosine of me, you got 2 over 3. So remember, cosine is adjacent over hypotenuse. And so what this says is, well, then your adjacent side must be 2 and your hypotenuse must be 3. And pursuing this a little bit further, we could say, what is y here? So we could say 2 squared plus y squared would be equal to 3 squared, or 4 plus y squared would be 9, or if we subtracted the 4, we get y squared equals 5, and then we get y equals plus or minus the square root of 5. I'll come back to the plus or minus in a second here. We would have to assess the situation here and say, okay, should it be the positive or the negative? In the first place, this was saying I am the cosine that gave me a positive 2 over 3. So with respect to positive 2 over 3, let's ask this question. Could I have drawn an angle? Remember the sum angle between 0 and pi. Could I have drawn my angle as some angle that would have landed over here and be a positive cosine of 2 over 3? And what I want you to see is that in this case, it would have been impossible. This would have been where cosine is negative 2 over 3. So because I know I'm in the first quadrant here, and that this is some positive angle here, when I say, now what's the tangent of this? What's the tangent of this? We could answer this question here. And so we say, what is the tangent of theta? And I'll rewrite this here, too. Let me write a little note here. Sketch the angle first. Sketch the angle first. And then let's say this here. Our second step would be to find the outer trig function value of that angle. The outer trig function value of the sketched angle. And so you can see that this is a piece of cake afterwards. If you were to say, what is the tangent of this angle here, theta, we've already sketched theta down here. We say theta is this angle. And so the tangent of this, now that we know y, has to be a positive root 5 here. We would say root 5 over 3. And so we just basically get root 5 over 3. And so let's throw this last one together. Just like we did this one here, we're going to draw an angle where sine is negative 3/5. And so I'd say, well, it's got to be some angle between here and here. And if it's negative 3 over 5, I suppose sine would have to be down here. And so it's this angle right here. I'm going to say here's theta, and theta is this angle right here, is sine inverse of negative 3 over 5. I'm going to try to squeeze this in here because what I've got to do is I've got to drop an altitude from here back to the x-axis. And so I apologize for my triangle kind of slicing over my inverse trig function here. But with this saying that sine was negative 3 over 5, it means that we know that the y value of our triangle is negative 3, and we know the r value here is 5. And so the only thing we don't know is x. We can clearly see that x would be positive here. Going back to Pythagoras, we say x squared plus y squared. We say negative 3 squared is, not plus, is 5 squared. We get this, we get x squared plus 9 is 25, and that x squared is 16. And if we take the square root of this, we get x is plus or minus the square root of 16, which is 4, and in this case we're going to keep the positive because it seems that after I've drawn this sketch, it has to be a 4. So now it's saying, let's go find the cosine of this angle theta, and the cosine of this angle, looking at this sketch, go find the outer trig function value, the cosine of that angle. We say the cosine is adjacent over hypotenuse, or we could say more generally, I'm going to write this down here, more generally x over r, and so we would get our x value is 4, and our r value is 5. So that's how you would evaluate those, draw a sketch. Cheers.